Somewhere in a basement laboratory in Santa Barbara, there is a small refrigerator that spends its days cooled to about 1/100th of a degree above absolute zero. Inside it sits a chip with 53 tiny superconducting circuits etched into its surface. Circuits cold enough and quiet enough that they begin to behave according to the strange rules of quantum mechanics rather than the ordinary rules that govern everything at room temperature. In January of 2022, a small group of physicists used 9 of those circuits to do something that, depending on how you choose to describe it, was either a fairly ordinary demonstration of quantum information transfer or the closest anyone has ever come to building a wormhole. That sentence sounds like it shouldn't be possible to say honestly. A wormhole, in the popular imagination, is a tunnel through space and time. The kind of thing that appears in science fiction to let a ship cross the galaxy in an afternoon. Nobody built one of those. Nobody bent space itself in a laboratory in California. What happened was something more abstract, and in its own way more interesting, because it rests on one of the strangest and most productive ideas in modern theoretical physics. The notion that certain quantum systems, when looked at through exactly the right mathematical lens, are not merely similar to gravitational systems. They are identical to them, not approximately similar. Not similar in some limit where you squint and ignore the details. Exactly, mathematically, interchangeably identical. You can write down the equations describing a cloud of particles doing ordinary quantum mechanical things in flat, gravity-free space, and by a precise mathematical transformation, those very same equations describe a black hole sitting inside a curved, gravitational spacetime 1 dimension higher. Same physics, 2 different descriptions of it, 2 faces of one underlying reality. Physicists call this idea holography, and the name is meant literally by analogy. A hologram is a flat 2-dimensional surface that, when you shine light through it correctly, projects out a full 3-dimensional image. All of the information needed to reconstruct the 3-dimensional scene is somehow encoded on a lower dimensional surface. The holographic principle in physics proposes something structurally similar, but far more sweeping, that all of the information describing what happens inside a region of curved spacetime, including everything that happens inside a black hole, can, in principle, be encoded on the boundary of that region. In a quantum system that lives in one fewer dimension and that has no gravity in it at all. This isn't meant as a loose metaphor. The way people sometimes say the brain is like a computer, the claim is that the 2 descriptions are mathematically the same theory, written in 2 different languages. If that's true, then a quantum system without gravity, properly understood, might secretly be a complete and faithful description of a gravitational universe with 1 more dimension. Study one, and in principle, you are studying the other. The foundational result behind this idea was worked out in the late 1990s by the Argentine-American physicist Juan Maldacena. He showed that a particular kind of quantum field theory living on the flat boundary of a region was precisely equivalent, not approximately equivalent, to a complete theory of gravity living inside that region. This equivalence became known as the anti-de Sitter conformal field theory correspondence, usually abbreviated as the ADES CFT correspondence. Anti-de Sitter space is a particular kind of curved spacetime with a specific geometric structure, and a conformal field theory is a kind of quantum theory with a special set of mathematical symmetries. Maldacena's original paper has gone on to be cited tens of thousands of times, making it one of the most influential single results in theoretical physics over the past 3 decades. What this means in practice, for anyone trying to actually do something with the idea, is this: if you can build the right kind of quantum system in a laboratory, and you look at it through the holographic lens, you might not just be studying an abstract quantum system. You might, in a very precise sense, be studying gravity. That possibility is what made the 2022 experiment conceivable in the first place. The particular quantum system the team chose to build is called the Sycamore model, and the name comes from the initials of three physicists whose work shaped it: Sabir Sachdev, Jinwoo Lee, and Alexei Kitaev. Sachdev and the originally proposed an early version of the model in the 1990s to study certain strange metallic materials in condensed matter physics, systems whose electrons behave in unusually disordered ways. Years later, Alexei Kitaev reformulated the model and noticed something about it that immediately caught the attention of anyone thinking about holography. The Sycamore model describes a collection of particles called Majranov, all interacting with one another in a very particular kind of random pattern. Every particle interacts with every other particle in the system, but the strength of each of those interactions is chosen randomly, drawn from a statistical distribution rather than following any orderly structure. The result is a system with no obvious geometric arrangement, no lattice, no preferred shape, nothing but a cloud of particles all talking to each other in a deliberately, maximally chaotic way. That chaos turns out to be exactly the point. In 2016, Maldacena, together with Douglas Stanford and Stephen Schenker, proved a result about quantum chaos that drew a sharp and unexpected line connecting the Sycamore model to gravity. They showed that every quantum system obeys a strict upper limit on how quickly information can scramble through it. Scrambling, in this context, describes the process by which a piece of information that starts out localized in one small part of a system gradually spreads out and mixes into the system as a whole, until it can no longer be found just by looking at any one local piece. It is the quantum analog of dropping a single drop of dye into a glass of still water. At first, the color sits in one place, then it begins to spread. Eventually, the whole glass is evenly tinted, and there is no way to point at any one region and say, that's where the dye went in. The rate at which this scrambling happens turns out to have a speed limit, one that depends on the system's temperature and on Planck's constant, the fundamental quantum of action that sets the scale for all quantum phenomena. No quantum system, no matter how it is built, can scramble information faster than this limit allows. And when physicists worked out the quantum properties of black holes carefully, they found that black holes sit exactly at that limit. Black holes are, in a precise technical sense, the fastest possible scramblers that nature permits. The Sycamore model, it turns out, scrambles at that same maximal rate. That is not a coincidence. It is the signature of the gravitational duality at work, a system that scrambles information at the absolute maximum possible speed is, when viewed through the holographic lens, mathematically identical to a black hole. This was the result that told physicists the Sycamore model might actually be useful as a laboratory stand-in for gravitational physics, not as a rough analogy, not as a toy, but as a precise mathematical dual. There was, however, a serious practical problem standing between this idea and an actual experiment. The full version of the Sycamore model requires a large number of fermions, all interacting with one another through a large number of randomly weighted connections. The number of interaction terms needed grows very quickly as the system gets bigger, and to get the kind of clean, genuinely gravitational behavior the theory predicts, you need hundreds of particles linked by hundreds of separate coupling terms. No quantum computer that existed in 2022 could handle that. Not the team's own Sycamore processor. Not anything else available anywhere in the world. If physicists wanted to study SYK physics on real existing hardware. They needed a way to shrink the model down to a manageable size, without destroying the very properties that made it interesting in the first place. That is where machine learning entered the picture. The team used a learning algorithm to prune the full SYK model, starting with the complete version and systematically removing interaction terms, keeping only the ones the algorithm judged essential for preserving the model's gravitational behavior. The goal was to find the smallest possible version of the system, using the fewest particles and the fewest interaction terms, that still showed the key signatures associated with holographic duality. This process produced what the team called a sparsified SYX model, with only 7 Majorana fermions and a small handful of interaction terms, small enough to fit comfortably onto 9 qubits of the Sycamore processor. The team then argued, based on careful calculations, that this stripped-down version had remained gravitationally faithful, that even after all the pruning, it still sat on the gravitational side of the holographic correspondence, that the machine learning process had found a genuine shortcut through the space of possible models without ever stepping off the holographic map. That argument seemed reasonable at the time the paper was published. It would later become the single sharpest point of contention in the entire story. The experiment also drew on a separate theoretical result, one worked out years earlier by the physicist Daniel Jafferis. In a 2016 paper written together with Ping Gao and Erin Wall, Jafferis showed something striking about entangled quantum systems. If you have 2 quantum systems that are already entangled with each other, sharing a kind of deep correlation that has no classical analog, you can couple them together in a very specific, carefully chosen way. That coupling, when translated through the holographic dictionary onto the gravitational side, looks like a burst of negative energy passing between 2 black holes. Negative energy matters here because of what general relativity says about wormholes. In the ordinary mathematics of general relativity, a wormhole connecting to distant regions of space-time is desperately unstable. Left alone, its throat pinches shut almost instantaneously, far too quickly for anything to pass through. But a carefully timed pulse of negative energy can prop that throat open, just long enough for something to slip through before it collapses again. This recipe, now known as the Gauge-Friswell mechanism, gave physicists a concrete description of what a traversable wormhole would look like. Translated into the language of the holographic dictionary, it is worth being precise about what this recipe actually was. It was not a blueprint for building an actual wormhole in real, physical space-time. Nobody was proposing to bend space itself. It was a recipe for running a particular quantum system that, when interpreted through the holographic correspondence, would behave exactly as if a wormhole had briefly connected to black holes. That is what the team set out to build using the Sycamore processor. Sycamore has 53 superconducting qubits in total, but for this particular experiment, only 9 of them were doing the actual work. Those 9 qubits were configured as 2 separate copies of the sparsified SYK model, one copy representing each side of a holographic universe containing a black hole. The 2 copies were first entangled with one another. Then the researchers applied the coupling pulse, the experimental stand-in for that negative energy shockwave predicted by the Gauge-Friswell mechanism. Then they waited, and then they watched for a signal. A single qubit of quantum information had been encoded into one side of the system before the pulse was applied. After the pulse, that same piece of information appeared on the other side. It had not been copied the way information sometimes is in classical computing. It had moved. In the language of quantum information science, this is called teleportation. And qubits being teleported from one place to another was, by itself, nothing new. That part of the result was already well established and well understood. What was new, and what made the experiment newsworthy, was the interpretation the team placed on it. They argued that this particular instance of teleportation had not happened through the ordinary, ho-hum quantum teleportation mechanism that had been demonstrated many times before. Instead, they argued, the information had effectively fallen into a black hole on one side of the system, passed through the throat of a wormhole connecting the two sides, and emerged from a second black hole on the other side. To support that more dramatic claim, the team pointed to 5 specific features of the data. Features, they argued, were gravitational fingerprints, signatures that an ordinary teleportation experiment would not produce, but that a genuine traversable wormhole would. The first was that the information appeared to scramble and thermalize in exactly the way it would if it had truly fallen into a black hole. The second was that the signal appeared only after a small delay, the kind of delay general relativity predicts for something crossing a region of curved spacetime, rather than appearing instantly. The third was that the signals from the two sides emerged in the correct causal order, consistent with information traveling through a connecting structure, rather than appearing all at once. The fourth, which the team singled out as their strongest piece of evidence, was a particular pattern in the data they called perfect size winding, which they described as the smoking gun. A signature, they argued, was specific to gravitational teleportation and nothing else. The fifth was that the coupling observed between the two sides matched the behavior expected from a negative energy shockwave. 5 fingerprints, by the team's own account, all pointing toward gravity. If their interpretation held up, this would have been the first time in history that a controlled laboratory experiment had produced a genuine piece of gravitational physics, not by building an actual black hole, which nobody had done or could do, but by building something that, through the precise mathematical correspondence of holography, was the same thing as a black hole and a wormhole, just viewed from the other side of the dictionary. The result landed on the cover of the journal, Nature, on the 1st of December, 2022. Major outlets covered it widely, and the institutional press release framed it as a first of its kind quantum gravity experiment running on an ordinary computing chip. For a few weeks, it felt to many people in the field as though gravity had finally, genuinely been dragged into a laboratory setting. Then, on the 15th of February, 2023, 3 physicists at the University of California, Berkeley, uploaded a paper to the preprint server. Their names were Bryce Cobrin, Thomas Schuster, and Norman Yao, and they were not outside critics unfamiliar with the territory. Yao runs a research group at Berkeley that works precisely at the intersection of quantum information, science, and gravitational physics. When the Nature paper appeared, Yao and his colleagues did what careful physicists are trained to do. They sat down and worked through the underlying mathematics, trying to understand exactly how a system as small as 7 interacting fermions could possibly be doing what the headlines said it was doing. What they found was a fundamental problem buried in the Hamiltonian, the mathematical object that describes how the sparsified SYK model evolves over time. The interaction terms in that stripped-down model, the Berkeley group discovered, all commuted with each other. In the language of quantum mechanics, 2 operations commute if the order in which you apply them makes no difference to the final result. If applying operation A and then operation B gives you the same outcome as applying B and then A, the 2 operations commute. This might sound like a small, technical detail, but its physical consequences turn out to be severe. To understand why, it helps to think about what scrambling and thermalization actually require at the level of these underlying mathematical operators. A system thermalizes, in the proper physical sense, when its different parts interact with each other in a chaotic, non-commuting way. The order in which different interactions happen genuinely matters. and the system's components become tangled together in a way that cannot be undone or separated out again. Information that starts out localized in one part of such a system spreads across all the other parts, because the parts are truly interfering with one another. A system whose operators all commute does not behave that way. Its different parts do not interfere with each other in that deep sense. Instead, they each evolve independently, in parallel, without ever genuinely mixing. It helps to picture the difference as the contrast between a room full of people having one loud, chaotic conversation, constantly interrupting and responding to each other, and a room full of people each wearing their own headphones, listening to a separate recording. In the second room, everyone is in the same physical space, and everyone is doing something at the same time. But nobody is actually responding to anybody else. The content in one person's headphones never makes its way into anyone else's experience. A fully commuting Hamiltonian, the Berkeley group argued, is the quantum equivalent of that headphones room. This created three specific, serious problems for the gravitational interpretation of the original experiment. The first problem concerned thermalization itself. The original team had listed scrambling and thermalization as one of their 5 gravitational fingerprints. The first piece of evidence that something genuinely black hole-like was happening inside the system. But a fully commuting Hamiltonian cannot truly thermalize, not in the rigorous sense the word requires. The mathematical conditions needed for true thermalization are precisely the kind of non-commuting, chaotic dynamics that a commuting system is structurally incapable of producing. So, the Berkeley group argued that the first fingerprint had never actually been present in the experiment. It only appeared to be present because the measurements being used to detect thermalization were not sensitive enough, on their own, to distinguish the real thing from a convincing imitation. The second problem concerned the supposed smoking gun. The pattern the original team had called perfect size winding and had described as their strongest and most distinctive piece of evidence. Kobrin, Schuster, and Yao showed that perfect size winding is not, in fact, specific to gravity at all. It is a generic feature that shows up routinely in small, commuting quantum systems for purely algebraic reasons that have nothing whatsoever to do with holography, black holes, or wormholes. The very signature the original team had built the most important part of their case around turned out to be a mathematical artifact of the simplification process itself, not evidence of gravity. The machine learning algorithm had produced a model small enough to fit on 9 qubits, and that smallness, combined with the commutativity it introduced, was what generated the pattern in the data. Gravity had nothing to do with it. This kind of mistake has a name among physicists, sometimes called the lamppost problem, after the old story about a man searching for his lost keys under a street lamp, not because that's where he dropped them, but because that's where the light is. You are looking for something specific. You simplify your system enough that you can actually analyze it, and then, without anyone intending it, the simplification process itself produces the very pattern you were originally hoping to find. Not because the pattern is a genuine signal from the thing you set out to study, but because it is a shadow cast by the act of simplifying. The third problem concerned the teleportation signal itself, the most basic piece of data in the whole experiment. When the Berkeley group examined the precise shape of that signal, not merely whether teleportation had occurred, but exactly how it evolved over time, they found that it did not match what you would expect from a qubit genuinely crossing a traversable wormhole inside a real gravitational system. The shape of the signal was wrong. Its detailed dynamics were inconsistent with what general relativity predicts for information traveling through an actual wormhole. So 3 of the 5 gravitational fingerprints the original team had reported were either absent altogether, or could be fully explained as properties of the simplification process. Rather than as genuine evidence of gravity, the reaction within the field was quiet but unmistakable. John Preskill, a theoretical physicist at Caltech who had not been involved with either group, told the science publication Quantum magazine that he felt the evidence for the gravitational interpretation was weakening. Vincent Hsu, a physicist at Berkeley working in exactly this area, put the sharpest version of the question directly on the table, asking whether the dream of studying quantum gravity in the laboratory was now effectively dead. Nobody had a clean, settled answer. The original team did not concede the point. They published a response arguing that even a fully commuting Hamiltonian could capture something physically meaningful, that even if the system was not fully and rigorously gravitational in the strict sense, it was not entirely without value either. Ping Gao, one of Jeffress's longtime collaborators, went further and wrote a separate paper proposing that what the experiment had actually demonstrated was a kind of pseudo-holographic behavior, something not quite full gravity in the rigorous sense, but also not a purely random, meaningless quantum system. He suggested the experiment had captured a regime somewhere in between, where a specific and unusual teleportation mechanism operates, distinct from both ordinary quantum teleportation and from the dynamics of a genuine traversable wormhole. The dispute sat unresolved in the preprint literature for more than 2 years. Then, in July of 2025, the journal Nature did something it does not do very often. It formally published the Berkeley critique as a peer-reviewed paper, placed in a special section the journal calls Matters Arising, alongside a formal reply from the original team. Matters Arising is the mechanism Nature uses for publishing serious scientific commentary on results it has previously published, and its existence is the journal's way of saying that a particular piece of criticism is significant enough to become a permanent part of the scientific record. The original 2022 paper was not retracted. It remains in the literature exactly as it was published, but attached to it now is a formal statement from 3 other physicists, stating plainly that 2 of the 5 claimed gravitational fingerprints were not actually present in the experiment, and that the 3rd had been generated by the simplification process rather than by anything resembling gravity. The original team's published reply acknowledged that many of the processes running on their learned Hamiltonian do not, in fact, have a clean gravitational description. They maintained, in that same reply, that some of those processes still do. So where does all of that leave the experiment, several years on? A qubit was that much is certain. The underlying data is the data, and nobody disputes it. But whether what happened inside those 9 qubits had anything genuine to do with a wormhole, in the sense the original headlines suggested, remains, as of this telling, an open question with serious and well-documented doubt attached to it. The most honest summary anyone in the field offers today is that the experiment showed something interesting. Whether that something was genuinely gravitational, or whether it was a clever, somewhat misleading toy model, has not been fully settled. And while that argument was still developing, quietly, in the background, someone else was running a much larger experiment, aimed at an entirely different and in some ways even more unsettling piece of physics. 5564 qubits. That is the number worth keeping in mind for this next part of the story. The wormhole experiment used 9 qubits. This second experiment used 5564. The 2 experiments ran on entirely different hardware, built by different teams, aimed at simulating a completely different physical system. But the sheer contrast in scale is striking on its own. And the question this second team was trying to answer is one physicists have been sitting with, somewhat uncomfortably, since the 1970s. The paper describing this experiment appeared in the journal Nature Physics on the 4th of February, 2025. The team was led by physicists at the University of Leeds, the Jülich Supercomputing Center in Germany, and the Institute of Science and Technology, Austria. The hardware they used was a D-Wave quantum annealer connected to computing systems at the Jülich Supercomputing Center, a fundamentally different kind of machine than a gate-based quantum computer like Sycamore, built around a different architecture and a different approach to quantum computation altogether. And the question they set out to ask was, in plain language, what does the end of the universe look like? The scenario they were modeling traces back to work done by the physicist Sidney Coleman in the late 1970s. Coleman was wrestling with a question that sounds deceptively simple. Is the universe stable? The naive answer seems obviously yes. The universe has existed for roughly 13.8 billion years. Galaxies have formed. Stars have burned steadily for billions of years. Atoms hold together. Everything appears, by any everyday measure, to be working just fine, but stable in the everyday, common-sense meaning of the word, and stable in the precise technical sense physicists use, are not the same thing in physics. A truly stable state is one sitting at the lowest possible energy configuration available to it. Picture a ball resting at the very bottom of a valley. If you push it slightly, it rolls right back down to where it started. That ball sits in a true energy minimum. But physical systems can also become trapped in what are called local minima, sometimes described as false vacuums. Picture instead a ball resting in a small depression partway up the side of a hill. From inside that depression, the ball looks perfectly stable. Give it a small push, and it rolls back to where it was. But somewhere further down the hill, there is a much deeper valley, a true global minimum, a lower energy state the ball has simply never reached. Given a strong enough push, the ball would leave its shallow depression, roll down the hill, and settle permanently into that deeper, lower energy valley. Coleman showed that this same basic logic applies to the quantum fields that fill the entirety of space, including the vacuum of our own universe. The ground state of quantum fields, such as the Higgs field and the electromagnetic field, might not actually sit at their lowest possible energy configuration. They might instead be sitting in a false vacuum, a local minimum that looks completely stable from the inside, but that quantum mechanics would, given enough time, eventually allow to tunnel out of. The tunneling process Coleman described would work something like this. Somewhere in space, entirely at random, a small region would spontaneously fluctuate into the true, lower energy vacuum state. A bubble of true vacuum would form. Inside that bubble, the fundamental constants of physics could be genuinely different from the ones we know. The masses of particles could shift. The relative strengths of the fundamental forces could change. Atoms might no longer hold together in any familiar or recognizable form, and ordinary chemistry might simply stop working. Once formed, such a bubble would expand outward at the speed of light, converting false vacuum into true vacuum everywhere it passed. You would never see it coming. The leading edge of the bubble would be traveling at exactly the speed of light, the same speed as any light that might otherwise carry advance warning of its approach. The two signals, the bubble itself and any light announcing it, would arrive at exactly the same moment. This is not idle science fiction speculation. It is a live, ongoing question in theoretical physics. Careful measurements of the Higgs boson's mass at the Large Hadron Collider, combined with equally careful measurements of the mass of the top quark, place the electroweak vacuum of the standard model of particle physics in a region physicists describe as not definitively stable, and not definitively unstable either, sitting uncomfortably close to the dividing line between the two, with meaningful uncertainty on both sides of that line. Coleman's original calculations suggested that the rate of this tunneling The probability per unit of volume per unit of time that any given patch of space would spontaneously nucleate a bubble of true vacuum was extraordinarily small. So small that the expected waiting time before such an event happened anywhere in our entire observable universe would be vastly longer than the current age of the universe itself. But those calculations carry substantial uncertainties of their own. And crucially, nobody had ever actually watched this kind of mechanism unfold, even inside a controlled, simplified model. That is precisely what the Leeds, Jülich and ISDA team set out to do. They arranged 5,564 superconducting flux qubits into a circular ring and configured them to behave according to its quantum Ising model, a well-understood framework from condensed matter physics that can be tuned to mimic a wide variety of different physical systems. By choosing the right parameters, they set the entire ring up to behave like a one-dimensional slice of a false vacuum, a deliberately simplified version of the full problem that nonetheless captures the essential physics of bubble nucleation and bubble expansion, without requiring a full three-dimensional simulation that no current hardware could handle. They then applied an external field designed to destabilize the false vacuum, analogous to artificially raising the tunneling probability, so that the process would unfold on a timescale short enough to actually observe. And they watched bubbles form. Quantized regions of the ring flipped over into a different state, the true vacuum configuration. In this simplified model, small bubbles nucleated first, then larger ones appeared. Some of these bubbles stabilized, some collapsed back down, some continued growing. At points, the team observed coherent bubble structures involving the equivalent of 300 separate spin flips spread across 300 qubits, all changing state together in a single, synchronized quantum process. The bubbles expanded outward within the ring. They interacted with one another. They collided. Some merged together. The entire sequence of dynamics played out coherently for more than 1 microsecond. A microsecond sounds vanishingly short, and in everyday terms it is. But for a quantum system of this size and complexity, it represents a remarkably long stretch of coherent behavior, corresponding to more than 1,000 of the fundamental time units that govern the qubit's own internal dynamics. That was long enough to study the detailed shape of bubble nucleation, measure the statistical distribution of bubble sizes, track their growth rates over time, and compare all of it directly against the theoretical predictions of quantum field theory in one spatial dimension. The match was good. The bubbles formed where the theory predicted they would form, and in roughly the way the theory predicted. The overall dynamics evolved as expected. The size distributions followed the predicted statistical patterns closely, and notably, nobody challenged this experiment the way the wormhole experiment had been challenged. The underlying physics here is far more conventional. The quantum Ising model is extremely well understood, mapped out across decades of work in condensed matter physics, and the behavior of the qubits matched the relevant equations in a comparatively direct, straightforward way that did not require any particularly controversial interpretive leaps. The experiment did, by all accounts, what it set out to do. But sitting underneath both of these stories, the contested wormhole experiment on one hand and the largely uncontested vacuum bubble experiment on the other, is a deeper question, one that the wormhole controversy forced out into the open, and that the field has not yet fully answered. How do you know, with real confidence, when a quantum simulation is actually showing you the truth? For most of the history of experimental physics, the answer to that question was simple and remarkably robust. You did the experiment, then someone else, somewhere else, with different equipment and a different team, did the same experiment again. If two independent laboratories arrived at the same result using genuinely different apparatus and different methods. The result was probably real. If they got different results from one another, somebody had made a mistake somewhere, and the field went looking for it methodically until the discrepancy was understood. That approach worked reliably for particle accelerators. It worked for telescopes. It worked across chemistry and materials, science, and nearly any field where you could, in principle, build a second copy of the apparatus and simply try again. It is starting to break down for quantum simulation. And the reason has to do with the entire point of using a quantum computer in the first place. The whole justification for simulating a physical system on a quantum computer, rather than on an ordinary classical computer, is that a classical computer cannot perform the same simulation efficiently. If a regular computer could simulate 100 FRMIN SYK model, or false vacuum decay across a system of 5,000 interacting qubits, nobody would need quantum hardware at all. You would simply run it on a laptop. A quantum computer earns its place in this story precisely in the regime where classical hardware fails to keep up, but that creates a genuinely uncomfortable situation. If your quantum simulation produces a surprising result about a wormhole, or about how vacuum bubbles form and grow, how exactly do you verify whether that answer is correct? You cannot simply run the same calculation on a classical computer and check. That was the entire problem you were trying to solve by turning to quantum hardware in the first place. Physicists call this the verification problem, and it has been quietly present in the field for years, acknowledged in papers, raised at conferences, noted in passing in review articles. The wormhole controversy brought it out into the open in a way that became impossible to ignore at its core. The verification problem connects to a deep question in computational complexity theory. Quantum computers are believed to be capable of solving certain kinds of problems exponentially faster than any classical computer ever could. But verifying that a quantum computer has actually produced the correct answer to one of those problems can be just as difficult as solving the problem classically in the first place. The same computational power that makes quantum simulation valuable is also exactly what makes quantum simulation difficult to independently certify. There are tools that help check specific, narrower aspects of how well a quantum device is performing. Cross-entropy benchmarking can measure how closely a device is producing the statistical distribution of outputs that theory predicts. Shadow tomography offers a way to estimate many different properties of a quantum state, using a relatively limited number of measurements. Randomized benchmarking helps characterize the error rates of individual quantum gates inside the processor. All of these tools are genuinely useful, but none of them provides a single, general, fully reliable way to certify that an arbitrary quantum simulation is faithfully reflecting the actual physical system it claims to be modeling. It helps to think carefully about what the Berkeley Group actually did when they challenged the wormhole result. They did not run the experiment again themselves. They did not build their own separate version of the wormhole circuit and compare results against the original team's data. Instead, they took the mathematics the original team had used, read through it with great care, and discovered that the model was not, in fact, doing what the original team believed it was doing. The check, in other words, was entirely theoretical. 3 physicists, working with pencil and paper, traced through the implications of a particular Hamiltonian and discovered that 2 of the claimed 5 gravitational fingerprints simply were not present, and that the third one was a mathematical artifact rather than genuine evidence of gravity. That is precisely the kind of issue peer review is supposed to catch before a paper is ever published. In this particular case, it surfaced publicly more than 2 years after the original paper had already appeared on the cover of Nature. The field in this instance, moved faster than the checking process could keep up with. In late 2025, a separate team at Swinburne University in Australia, led by a researcher named Alexander, reported a new technique for validating the outputs of a different kind of quantum machine altogether. Devices called Gaussian boson samplers. These are specialized photonic quantum computers, built using light rather than superconducting circuits, designed to perform one particular kind of calculation believed to be extremely hard for any classical computer to replicate. When the Swinburne team applied their new validation method to a previous, widely celebrated landmark experiment in Gaussian boson sampling, one that had been treated as a genuine milestone in the field, they found errors. Unexpected ones. Errors that nobody had spotted before in a result that had already been celebrated as a major achievement. This Swinburne result does not directly say anything about the wormhole experiment or about the false vacuum simulation. It involves a completely different machine and a completely different underlying problem, but it points squarely at the same underlying nerve running through the field. Quantum computers are now routinely doing things that nobody can independently check using classical methods. And whenever the field develops new tools capable of checking them after the fact, those tools keep revealing that the underlying picture is messier and less certain than the original headline suggested. There is something structurally familiar about this pattern, something that echoes the early history of computational simulation in other scientific fields entirely. Climate modeling went through a version of this same dynamic, where increasingly powerful simulations outpaced the tools available for validating them. Protein folding prediction went through something similar. Economic forecasting went through it as well. In each of these cases, the simulation tools themselves advanced faster than the methods developed to check them, and it took years of careful work to clearly separate the question of whether a model produced a particular output from the much harder question of whether that model was telling researchers something genuinely true about the real world. Quantum simulation may now be moving through its own version of that same reckoning. The path forward through this uncertainty is not, in itself, mysterious. The field broadly knows what kinds of tools are needed. Tighter mathematical guarantees about how faithfully a simplified model represents the full system it is meant to stand in for. Better validation tools, ones that can certify not merely that a quantum device is operating within its hardware specifications, but that the specific simulation it is running is actually a faithful representation of the physical system it claims to model. And a cultural shift toward publishing not just the striking headline result, but the full diagnostic picture surrounding each experiment, including an honest accounting of the limitations built into the simplifications used, the actual range of parameter space that was explored, and a clear list of which checks were performed and which were not. The false vacuum simulation at Jülich, by most accounts, is solid work. The bubbles formed where theory predicted. The dynamics matched the underlying equations closely. The path toward a genuine three-dimensional version of the experiment is real, and researchers are actively working toward it. What the SYK model and the broader holographic program have shown, despite all the controversy surrounding the wormhole results specifically, is that the conceptual bridge between quantum information and gravity is no longer merely a theoretical construction sitting on paper. It is becoming something that can be probed, however imperfectly and with however much difficulty, inside an actual laboratory. The question sitting at the heart of holography, whether space-time itself somehow emerges from the entanglement structure of quantum systems, is no longer a question confined entirely to paper and pencil. It is beginning, in a real, if still tentative sense, to be the kind of question you can build an experiment around. That genuinely is something new. But the Sycamore experiment also taught the field a lesson that the excitement of the original moment nearly obscured entirely. A teleportation signal is not, on its own, a wormhole, even if the underlying mathematics technically allows you to interpret it that way. A pattern appearing in a dataset is not automatically a gravitational fingerprint simply because someone has chosen to call it one. A 9-qubit experiment running for a few seconds on a chip in California is not, by itself, a confirmation that space-time emerges from quantum information, no matter how appealing that conclusion might be to believe. The deeper questions remain exactly as open as they were before any of this began. Nobody knows whether the space-time we actually inhabit is holographic in the full, rigorous technical sense the mathematics sometimes suggests. Nobody knows whether our own universe is sitting inside a metastable false vacuum, with the fundamental constants of physics balanced on a knife's edge that quantum mechanics might, eventually, tip over. Nobody knows whether the next generation of quantum simulations, running on machines with thousands or eventually millions of qubits, will produce results that genuinely illuminate these deep questions, or whether they will instead produce results that look like answers right up until someone reads the underlying mathematics carefully enough to find the hidden artifact. What can be said with confidence is this: somewhere in Santa Barbara, a small dilution refrigerator is quietly humming away with 9 qubits inside it. Somewhere in Jülich, a different machine is running with 5,564 qubits inside it. And somewhere in dozens of other laboratories scattered around the world, physicists are configuring quantum systems to ask questions about gravity, about vacuum stability, and about the deep underlying structure of space-time that had genuinely never been asked inside a laboratory before any of this began. The answers coming out of these efforts are not always reliable yet. The tools needed to check them are catching up, slowly. The culture of the field is gradually adjusting to a new regime, one in which the available machinery has outrun the available methods for confirming what that machinery is actually telling us. But the underlying questions themselves remain entirely real. The tension between quantum mechanics and gravity, the two most successful theoretical frameworks in the history of physics, frameworks that cannot both be correct in their current form, stands as the deepest open problem in all of fundamental physics. To understand why the wormhole experiment landed with the kind of force it did, it helps to understand what had been quietly building in theoretical physics for more than 2 decades beforehand. The holographic principle did not appear out of nowhere. It emerged gradually, out of a series of increasingly uncomfortable encounters between general relativity and quantum mechanics, to theories that each work extraordinarily well inside their own respective domains, and that have stubbornly, persistently refused to be reconciled into any single, coherent framework that covers both. General relativity describes gravity. It explains how mass and energy curve the underlying fabric of space-time, and how that curvature, in turn, tells matter how to move through it. It governs the orbits of planets, the behavior of black holes, and the large-scale expansion of the universe itself. Its predictions have been tested to a remarkable degree of precision. Gravitational waves, first directly detected in 2015 and attributed to the merger of 2 black holes, located more than 1 billion light-years away, matched the predictions of general relativity to an extraordinary degree of accuracy. By every available test, the theory simply works. Quantum mechanics, meanwhile, describes essentially everything else. It explains how particles behave at the smallest accessible scales, how atoms interact with one another, how light is emitted and absorbed, how chemical bonds form and break. It underlies the operation of every semiconductor, every laser, and every nuclear reaction. Its predictions are, by a wide margin, the most precisely verified predictions in the entire history of science. The magnetic moment of the electron, a quantity describing how strongly the electron behaves as a tiny magnet, has been both measured experimentally and calculated theoretically to more than 10 decimal places. And the measured value and the calculated value agree. That theory, too, simply works. But when physicists try to combine the two frameworks, when they try to apply the methods of quantum mechanics directly to the gravitational field itself, everything falls apart. The calculations that result produce answers that are infinite, not merely very large, but genuinely, mathematically infinite. The standard technique physicists normally use to tame infinities that show up in quantum field theory, a procedure called renormalization, simply fails when applied to gravity. The resulting theory is what physicists describe as non-renormalizable, meaning the infinities cannot be systematically tamed using the usual mathematical tools. This is not a minor technical hiccup that careful bookkeeping can eventually patch over. It means that our two best theories of how the universe actually works are, at some deep level, fundamentally incompatible with one another. At some fundamental level, either one of them is simply wrong, or both of them are incomplete, or both of them are merely approximations to some deeper underlying theory that nobody has yet discovered. This incompatibility is the central open problem of theoretical physics, and the holographic principle, along with the anti-de Sitter, conformal field theory correspondence that Maldacena discovered, represents the closest thing the field currently has to a path toward resolving it. It is worth being clear about what the holographic correspondence does not do. It does not directly solve the underlying incompatibility between quantum mechanics and gravity. It does not hand physicists a single, fully unified theory of quantum gravity, one that smoothly reduces down to general relativity in one limit and to ordinary quantum mechanics in another. What it offers instead is a precise mathematical dictionary, a dictionary connecting a quantum theory that has no gravity at all to a separate gravitational theory living in one additional dimension. It says, in effect, that these two seemingly very different things are, mathematically, the same thing that is not quite the same achievement as full unification. But it is something genuinely significant in its own right. It means you can, in principle, take a question about gravity, translate it through the dictionary into an equivalent question about quantum mechanics, and the quantum mechanical version of the question might turn out to be tractable in situations where the original gravitational version was not. The reverse direction works too. You can take a question originally framed in terms of quantum systems, translate it into a gravitational question, and the geometric intuition available on the gravity side might reveal something the original quantum calculation had kept hidden. This dictionary has already proven enormously productive across theoretical physics. It has been used to study strongly coupled quantum systems in condensed matter physics, the behavior of quark-gluon plasmas produced in heavy-ion collisions, and various properties of black holes. In many of these applications, one side of the correspondence offers a noticeably easier calculation than the other, and physicists simply choose whichever description happens to be more tractable for the particular problem at hand. But there has always been a significant question hanging over the entire program. Does the holographic correspondence, in its original and most rigorously understood form, actually describe our own universe? The original anti-de Sitter, conformal field theory correspondence was worked out specifically for a particular type of spacetime, called anti-de Sitter space, a geometry characterized by a negative cosmological constant. Our actual universe, as best as anyone can currently measure, appears to have a positive cosmological constant instead. It is described not by anti-de Sitter space, but by what is called de Sitter space, a geometry that differs from anti-de Sitter. space in genuinely important ways, whether the holographic principle extends cleanly to de sitter space, whether there exists a precise version of a so-called CFT correspondence that actually describes the universe we live in, remains a major unsolved problem in theoretical physics. So the holographic program currently occupies a complicated epistemic position. It is, by any measure, an extremely powerful mathematical tool. It is almost certainly telling researchers something genuinely deep about the relationship between quantum mechanics and gravity. But whether it is literally exactly true of the specific universe we happen to inhabit, or whether it instead describes a precise mathematical duality that applies cleanly to a different kind of space-time than the one we live inside, remains genuinely unclear. The wormhole experiment, at its heart, was an ambitious attempt to make this abstract correspondence concrete, to build something real inside a laboratory that would force the holographic dictionary to make a specific, testable, falsifiable prediction. If the experiment had worked exactly as advertised, it would have meant that the holographic dictionary was not merely an elegant mathematical tool, but something closer to a physical reality that could be directly probed using laboratory equipment. That is precisely why the stakes felt so high to many people in the field, and why the Berkeley critique, once it finally arrived in its fully formal published version, felt so deflating to certain corners of the field. It is worth being precise here too. Nobody discovered that holography itself was wrong. The underlying mathematical correspondence remains entirely solid. The SYK model is still genuinely dual to a gravitational system in the appropriate mathematical limits. The Gauge-Friswall mechanism remains a valid theoretical result, exactly as it was before the controversy began. None of that changed at all. What changed was a much narrower and more specific claim. The claim that this particular experiment, running this particular stripped-down model, had actually managed to cross the line separating ordinary quantum information processing from genuine gravitational physics. It had not, at least not clearly, and not in the way the original team had argued. The sparsification process, the machine learning step that had made the entire experiment possible in the first place by fitting the model onto just 9 qubits, had produced a model that looked gravitational in several respects. But that was commuting in a way real gravitational systems are not. The simplification, in trying to make the model small enough to actually run, had inadvertently cut out the very ingredient that made the gravitational behavior genuine in the first place. That is an uncomfortable lesson, but it is worth being clear about what kind of lesson it actually is. It is not a lesson about whether holography itself is real. It is a lesson about the gap, often invisible from the inside, between a system that is genuinely holographically dual to gravity and a system that merely resembles such a system in certain respects, while quietly failing to capture the full underlying structure. That gap can be entirely invisible inside a simplified model, and in quantum simulation, simplified models are, for the foreseeable future, essentially all anyone has available to work with. This connects to a much older problem in experimental physics, one that tends to receive less attention than it probably deserves. The problem of model validity. Every experiment, in every field, involves some kind of model. Nobody measures nature directly, in some pure and unmediated way. Researchers measure a physical system they have built or found, apply a theoretical framework in order to interpret what the measurement means, and then report a result. That result is only ever as good as the combination of the measurement itself and the theoretical framework used to interpret it. If the framework contains a hidden flaw, the final result inherits that flaw, whether or not anyone notices. This is true across every field of experimental science. In most ordinary experiments, the theoretical framework being used is already well established, and the main source of uncertainty lies almost entirely in the measurement itself. You already know what you are measuring. You simply need to measure it precisely enough. But in quantum simulation, both sides of that equation carry large uncertainty simultaneously. The hardware itself is noisy. The qubits make errors. The gates are imperfect. And at the same time, the theoretical model actually being simulated has typically been simplified in ways that may or may not preserve the essential physics anyone actually cares about. Both the measurement and the underlying theoretical framework are uncertain at the same time, and managing that double uncertainty has become one of the central challenges the field is now working to address. Doing so requires a different style of experimental reporting than physics has traditionally relied on. Not simply, here is the signal we observed, and here is what we believe it means, but something considerably more thorough. Here is the precise model we were actually using. Here is how we confirmed, as carefully as we could, that our simplification preserved the essential physics we cared about. Here is the specific range of parameters over which we verified the correspondence held. Here are the checks we actually ran, and just as importantly, here are the limits of what we can honestly claim based on those checks. The original Wormhole paper, in retrospect, was not written in quite that style. It was written in a style that treated the holographic interpretation as something already established, rather than as a claim still very much in need of testing. The 5 gravitational fingerprints were presented as evidence supporting the interpretation, rather than as outputs that still needed to be independently verified against the actual requirements that interpretation demanded. The Berkeley group found the gap between those two very different modes of scientific presentation, and that gap turned out to matter quite a lot. It helps to return now to the false vacuum experiment, because it illustrates this same underlying issue from a genuinely different angle, and because the physics it is probing is on its own terms extraordinary. The idea of a false vacuum is one of the stranger implications buried inside quantum field theory. In classical physics, the word vacuum simply means empty space, nothing there at all. In quantum field theory, vacuum instead means the lowest energy state available to a quantum field. And that lowest energy state is not actually nothing. It is a specific, well-defined quantum state with its own particular properties. And different quantum fields can have entirely different vacuum states. The Higgs field, which is responsible for giving fundamental particles their mass through what is known as the Higgs mechanism, has a vacuum state in which the field itself takes on a specific non-zero value throughout the entirety of space. That particular vacuum expectation value is what breaks what physicists call electroweak symmetry, and in doing so, gives the W and Z bosons their respective masses. The natural question that follows is this: is the Higgs field currently sitting at its absolute lowest possible energy state? Or is it instead sitting inside a local minimum, a valley that is stable enough for now, but not quite the deepest valley available, with a genuinely lower energy configuration sitting somewhere beyond an intervening energy barrier? One the field could in principle tunnel through, given enough time. The answer to that question depends on the precise, measured value of the Higgs boson's mass and the measured mass of the top quark, both of which experimentalists can measure directly. When physicists use the currently measured values to work out the detailed shape of the Higgs potential, what they find is that our current vacuum state does technically sit in a local minimum, but the global minimum of that same potential appears to lie at a much lower value of the field. A bubble of true vacuum, if one ever formed, would have the Higgs field sitting at a dramatically lower value inside the bubble than it currently sits in our own vacuum. The electroweak scale, the characteristic energy scale at which the Higgs mechanism operates, sits at roughly 246 billion electron volts. The scale associated with the true vacuum, if the metastability calculations are correct, would sit many orders of magnitude higher in energy, somewhere in the neighborhood of 10 to the power of 11 billion electron volts. An energy scale far beyond anything the Large Hadron Collider is capable of probing directly. This means the energy barrier separating our current false vacuum from the true vacuum is extremely large, and tunneling through a barrier that large is correspondingly rare. The rough estimate physicists currently give for the vacuum's expected lifetime, meaning the expected waiting time before a bubble spontaneously nucleates anywhere within our observable universe, comes out, in some calculations, to longer than 10 to the power of 100 years. The current age of the universe, by comparison, is roughly 14 billion years, or about 10 to the power of 10 years. So the estimated vacuum lifetime is many, many orders of magnitude longer than the current age of the universe itself. By some estimates, it is even longer than the time it would take every black hole in the entire observable universe to fully evaporate through Hawking radiation, a process that is itself almost inconceivably slow. But these calculations carry enormous uncertainties of their own. The estimate of the vacuum's lifetime depends extremely sensitively on the precise measured values of the Higgs boson mass and the top quark mass, and both of those measurements carry their own experimental uncertainties. Small shifts in either measured value can shift the calculated vacuum lifetime by many orders of magnitude in either direction. The current measurements sit frustratingly close to the boundary between stability and metastability, and the uncertainty bands surrounding the measured masses straddle that dividing line in ways that genuinely leave it unclear whether the electroweak vacuum is stable, metastable, or even, by some readings, technically unstable outright. This uncertainty is not merely a technical footnote. It touches on a fundamental question about the nature of the ground state of our universe itself. If the vacuum is truly stable, the universe could, in principle, persist forever in its current form, at least until much later. Far slower processes such as proton decay and the gradual evaporation of black holes eventually reduce it to some final equilibrium state. If the vacuum is instead metastable, there is a non-zero probability, per unit of space-time volume, of a bubble forming somewhere in the universe at any given moment. That probability is small enough that it almost certainly has not happened yet, and almost certainly will not happen for an extraordinarily long time to come. But it is not exactly zero. And there is one more uncomfortable wrinkle worth mentioning. The calculation of vacuum stability assumes that the standard model of particle physics is exactly correct, with no new physics appearing at any energy scale beyond what has already been measured. If there are additional particles or additional forces lying beyond the standard model not yet discovered, they could in principle modify the shape of the Higgs potential in ways that either stabilize the vacuum further or destabilize it even more than current estimates suggest. Nobody currently knows whether that is the case. The Large Hadron Collider has found no clear evidence of new physics beyond the standard model at the energy scales it is currently able to probe, but the absence of evidence at those particular scales does not mean such new physics doesn't exist somewhere beyond reach. This is the backdrop against which the false vacuum simulation needs to be properly understood. The researchers working at Leeds, Jülich, and ISTEA were not simply running an interesting quantum simulation for its own sake. They were, in a small and carefully bounded way, building a laboratory version of a mechanism that might ultimately determine whether our own universe is permanent or merely long. The scale difference between their simulation and the real cosmological problem remains enormous. 5,564 qubits arranged in a simple, ring is not remotely the same thing as a quantum field, filling the entirety of three-dimensional space across the whole observable universe. One spatial dimension is not the same as three. A microsecond of coherence is not a cosmological timescale, but the underlying mechanism is the same. Quantum tunneling out of a metastable state into a lower energy state. Bubble nucleation. Coherent growth. Expansion. Collision. The dimensionality and the overall scale differ enormously between the toy experiment and the real cosmological question, but the physics governing the transition itself is described by the same underlying equations in both cases. Watching that transition happen for the first time inside a controlled quantum system gives theorists a genuine way to check their calculations against an actual measurement, rather than relying purely on paper and pencil estimates. The theory predicts where bubbles should nucleate and how quickly they should grow. The experiment shows where they actually do nucleate and how quickly they actually do grow. That comparison, carried out carefully, is the science itself. What the team found was that the theory was right. The predictions of quantum field theory in one spatial dimension matched the observed behavior of the qubits closely. The distribution of bubble nucleation sites, the growth rates of individual bubbles, the dynamics of bubble collisions, all of it matched the theoretical predictions. That is a genuine experimental result. It is not, on its own, a claim about our actual universe's vacuum stability, but it stands as a meaningful check on the theoretical machinery that would eventually be used to make such claims, carried out in a regime where that machinery can actually be tested directly against data. The fact that nobody challenged this particular experiment, the way the wormhole experiment was challenged, is, on its own, informative. The Ising model is well understood, mapped out over decades of careful theoretical and experimental work. The behavior of a quantum annealer running an Ising model is comparatively well characterized. The mapping from the physical dynamics of the qubits to the mathematical model of false vacuum decay is cleaner and more direct than the mapping from the sparsified SYK model all the way to holographic quantum gravity. This difference points toward something genuinely important about the current state of quantum simulation as an experimental method. Not all quantum simulations are equally difficult to validate. Some physical systems are understood well enough that a quantum simulation of them can be checked against several independent lines of evidence at once. Classical limits that hold in certain parameter regimes, exact mathematical solutions available for small system sizes, symmetry arguments, direct comparison with related systems that have already been studied using other independent methods. The false vacuum simulation fits comfortably into this category. It is a genuinely hard simulation to run, but it is a simulation of a system theorists already understand well enough to make precise, falsifiable predictions about in advance. The holographic gravity simulation sits in a fundamentally different position. The version of the holographic correspondence relevant to the SYK wormhole experiment does not have a clean classical limit that can be checked against in any straightforward way. The mapping from quantum information to gravity is, on its own, a non-trivial theoretical step, requiring real care and real mathematical machinery. The sparsification process adds yet another layer of theoretical uncertainty on top of that. The end result is a chain of theoretical interpretations, each one carrying its own independent uncertainty, with the final claim that the experiment demonstrated genuinely gravitational behavior, sitting at the very end of that long chain, where every single link needs to be independently justified for the whole argument to hold. That is not, in itself, an impossible standard to meet. Theoretical physics regularly makes predictions through long chains of careful mathematical reasoning, and experiments regularly succeed in testing those predictions. But when the chain is long and the individual links within it are not all equally solid, the experimental result being used to support the conclusion needs to be more than a single piece of data that happens to fit comfortably with the preferred hypothesis. It needs to be a result that is genuinely difficult to fit to any plausible alternative hypothesis. A result specifically inconsistent with the non-gravitational interpretation and specifically, distinctively consistent with the gravitational one. The Berkeley group showed that the most important single piece of evidence the original team had offered in support of the gravitational interpretation, the perfect size winding signature, was in fact equally consistent with the non-gravitational interpretation. In fact, it turned out to be a direct prediction of the non-gravitational interpretation specifically. That is a considerably stronger and more damaging result than simply casting general doubt on a claim. It is showing, with some precision, that the evidence the original team relied on most heavily was actually pointing in the wrong direction the entire time. There is, however, a genuinely productive way to read the full history of this experiment and its aftermath. The original paper was ambitious, internally rigorous on its own terms, and genuinely novel in its conception. Nobody had ever attempted an experiment quite like it before. The team worked out a sophisticated theoretical framework, reduced it down to something that could actually run on real, existing hardware, ran it, and reported a result that matched their own theoretical expectations going in. That, on its own terms, is good science. The Berkeley critique then found a genuine flaw buried inside that theoretical framework. That, too, is good science. The formal matters arising exchange gave both groups the opportunity to put their respective arguments permanently on the scientific record. That is, the error correction mechanism of science doing precisely what it is supposed to do. The genuinely uncomfortable part of this story is the timeline. The original paper was published in December of 2022. The Berkeley critique appeared on the preprint server arXiv in February of 2023. Only a few months later, the formal matters arising response was not published in Nature until July of 2025, 2.5 full years after the original critique had already circulated publicly. During those 2.5 years, the claim that physicists had built a traversable wormhole on a quantum chip circulated widely in public discourse, was cited in educational materials, appeared in review articles, and meaningfully shaped how the broader field talked about the future prospects for quantum simulation of gravity. The mechanism that eventually corrected the record worked, in the end, but it worked slowly. And it is worth genuinely sitting with the question of whether that correction mechanism would have worked at all, on any reasonable timescale. If the original claim had been less dramatic and less publicly visible, there is a long history within physics of experiments, whose technical details were reported entirely correctly, but whose interpretation remained contested for years or even decades afterward. The discovery of the positron in 1932 by Carl Anderson offers one clear example of an experiment where the underlying data was correct, and the interpretation, while initially radical, eventually turned out to be entirely right. The positron is now a completely standard part of the particle physics toolkit, and nobody questions its existence today. The early history of attempts to directly detect gravitational waves offers a different kind of cautionary example. Joseph Weber, who built the very first gravitational wave detectors back in the 1960s, reported detections that other independent research groups simply could not replicate. The interpretive claims he made did not ultimately hold up, even though the experimental engineering work behind them was genuine and, in its own way, quite innovative for its time. A pattern shows up across these historical cases, one worth taking seriously here. New experimental technologies, whenever they become powerful enough to probe genuinely unprecedented physical regimes, tend to produce results faster than the surrounding scientific community can fully and critically evaluate them. The detectors involved are often sensitive enough that almost any output starts to look potentially real and meaningful. The theoretical frameworks needed to properly interpret that output are frequently not yet fully worked out. The professional incentives within the field tend to push toward publishing striking results quickly, while the machinery needed for careful, thorough validation remains underdeveloped, often simply because nobody has needed it badly enough before. Quantum simulation today sits in exactly this kind of position. The devices involved are now powerful enough to do things no classical computer can replicate. The theoretical frameworks needed to properly interpret their results are still very much being worked out in real time. The incentives present in modern academic physics, shaped by funding structures, journal prestige, and public attention, tend to push researchers toward dramatic, headline-friendly claims, and the tools available for careful validation remain, by most honest accounts, years behind the tools available for raw computation. This is not meant as a criticism of any individual physicist or any individual research group involved in this story. It is better understood as a structural feature of an entire field passing through a particular phase of its own development. The wormhole experiment was carried out by excellent physicists, using the best hardware available to them at the time, working from a genuinely sophisticated theoretical framework, and reporting results that matched their own theoretical expectations going in. The Berkeley critique was carried out by equally excellent physicists, who read the original paper with real care and found a genuine problem the original team had simply missed. The Swinburne validation work was carried out by physicists tackling the general problem of quantum simulation verification on its own terms, entirely independent of any one specific experiment. None of these groups made mistakes in the sense of being careless or dishonest about their work. The system, taken as a whole, worked eventually. The open question is whether it will continue to scale as quantum computers grow larger and more capable. As the simulations these machines can run move further and further beyond anything a classical computer could check directly, the resulting experiments will become correspondingly harder to evaluate. The theoretical frameworks needed to interpret them will grow correspondingly more complex. The gap between publishing a striking result and properly validating that result will keep widening, unless the field develops genuinely better tools and genuinely better norms for managing that gap as it grows. Some of those tools are already being developed. Classical simulation techniques are themselves steadily improving, which helps verify quantum simulations in the regimes where the two approaches still overlap. Error mitigation and error correction techniques are advancing as well, which helps distinguish genuine quantum computation from ordinary hardware noise masquerading as a signal. New theoretical methods for directly checking holographic correspondence in specific, well-chosen models are being actively developed by several groups. The community, broadly speaking, is well aware of the problem. The professional norms governing how results get published and discussed are changing considerably more slowly. Scientific culture tends to be conservative, and generally for good reasons. Norms that have worked well across a long stretch of time do not change quickly, and they should not change carelessly. The long-standing norm of reporting a striking result and then letting the broader scientific community evaluate it carefully over time has worked reasonably well across most of the history of physics. It may well need real modification for the specific case of quantum simulation, in a way that has not yet fully happened. It is worth considering, concretely, what it would actually take to convincingly demonstrate quantum gravity in a laboratory setting, not inside a toy model, not through a sparsified proxy standing in for the real thing. a genuine holographic correspondence between a real quantum system running in a lab and a gravitational system, featuring real black holes and real space-time geometry. What would that actually require? The most straightforward answer is that researchers would need a quantum computer large enough to run a fully faithful version of the SYK model, without any sparsification step at all. Not 7 Majorana fermions connected by a small handful of interaction terms, but hundreds of Majorana fermions linked by the full, complete set of random interactions the original theoretical model calls for. A system that genuinely saturates the quantum chaos bound across all of its available degrees of freedom, rather than only inside a carefully simplified proxy. That kind of system would eliminate the central ambiguity at the heart of the current controversy, the question of whether any observed gravitational behavior is genuinely real, or merely an artifact produced by the simplification process itself. How many qubits would something like that actually require? The full SYK model, with a number of Majorana fermions, denoted n, requires a mathematical space whose dimension grows as 2 raised to the power of n divided by 2. For n equal to 100, that works out to a space with dimension of roughly 10 to the power of 15. Running a genuinely faithful quantum simulation of a system that large would require something in the range of 50 to 100 logical qubits, equipped with full, fault-tolerant quantum error correction. The best quantum computers currently available have hundreds of physical qubits, but only a small handful of true logical qubits, because many individual physical qubits are needed to encode and protect each single logical qubit from the accumulation of errors over time. Current leading estimates for when quantum computers featuring hundreds of usable logical qubits might actually become available range from the early 2030s out to the middle of that decade. Some more optimistic projections place the timeline somewhat earlier. Some more conservative projections push it out considerably further. But the broad consensus across the field is that the underlying hardware is improving along a trajectory that will eventually reach that scale. When that scale is finally reached, the original wormhole experiment and its long controversy will likely look quite different in hindsight. The argument over whether the sparsified model was genuinely holographic will be replaced by an experiment running on a system that is unambiguously holographic by direct construction, with no sparsification step left to argue about. The teleportation signal observed in that future experiment will be a genuine result from a true traversable wormhole analog, rather than from a carefully constructed commuting proxy standing in for one. The gravitational fingerprints physicists look for will either be genuinely present or they will not be, and in either case, the answer will be a meaningful and informative one. That future experiment might end up confirming that the original interpretation was essentially correct all along, that the sparsified model had, despite its simplicity, captured enough of the genuine holographic structure to produce real gravitational teleportation, even if an imperfect version of it. Or it might instead confirm that the Berkeley critique was right, that genuine holographic behavior requires the full, non-commuting chaos of the complete SYK model, and that no shortcut through sparsification can ever fully substitute for that. Either outcome would be valuable. Meanwhile, the false vacuum research program is moving forward in its own separate direction. The Leeds, Jülich, and ISDA teams' one simulation is explicitly framed as a stepping stone toward eventual two-dimensional and three-dimensional simulations. The path toward those higher dimensional versions involves larger quantum annealing, with qubits arranged not in a simple ring, but in two-dimensional and eventually three-dimensional lattice structures. Each additional spatial dimension brings the simulation closer to the actual geometry of our universe, and correspondingly further from any regime where a classical computer could independently check the results. The physics question those future simulations are ultimately targeting is whether quantum fluctuations in the very early universe could have seeded a population of true vacuum bubbles, bubbles that grew and collided with one another, and whether that early process might have left any observable signature behind in the cosmic microwave background, in the large-scale distribution of galaxies, or in the properties of gravitational waves that might one day be detected. Current astronomical measurements show no clear evidence of false vacuum decay having occurred in the early universe, but the theoretical predictions of what such a signature would actually look like depend on calculations that are extremely difficult to carry out analytically. Using pencil and paper alone, quantum simulation could, in time, make those calculations genuinely tractable for the first time. D-Wave's most recent generation of quantum annealers uses what are called Pegasus and Zephyr topology graphs, which allow for certain specific patterns of qubit connectivity, but not others, mapping a genuinely two-dimensional or three-dimensional false vacuum simulation onto the connectivity patterns available on real hardware requires clever graph embedding techniques, and those techniques introduce their own additional layer of theoretical uncertainty that researchers need to carefully track. Groups at several universities and national laboratories around the world are actively working on this mapping problem right now. There is a third frontier within this broader story worth following closely, one that receives somewhat less public attention than either wormholes or vacuum decay, but that may ultimately prove more foundational than either. It concerns the question of what entropy actually means inside a theory of quantum gravity. Black holes, it turns out, have entropy. The entropy of a black hole, first calculated by Jacob Bekenstein and Stephen Hawking back in the 1970s, turns out to be proportional to the surface area of the black hole's event horizon, rather than to the volume of the region contained inside it. This is, on its face, deeply strange. For ordinary physical systems, entropy is what physicists call an extensive quantity, meaning it scales with the overall volume of the system in question. A gas confined inside a box has entropy proportional to the volume of that box, in the way you would naturally expect. But a black hole's entropy instead scales with the surface area of its horizon, not with the volume of whatever lies inside it. This unexpected area scaling turns out to be one of the key observations that originally led physicists toward the holographic principle in the first place. The total information content of any given region of spacetime, it turns out, is bounded not by the volume of that region, but by the area of its boundary. This relationship is known as the Bekenstein-Hawking bound, sometimes also called the holographic entropy bound, and it means that spacetime cannot, even in principle, contain arbitrarily large amounts of quantum information packed into a given unit of volume. The maximum possible density of information is instead bounded by the surface area through which that information can be accessed from outside. When Maldacena originally worked out the anti-die sitter conformal field theory correspondence, one of the very first and most important checks on whether the correspondence was actually correct was whether it properly reproduced this known entropy formula for black holes. The entropy calculated on the gravitational side, derived directly from the area of the event horizon, needed to match the entropy of the corresponding quantum field theory state, calculated independently through entirely standard quantum mechanical methods. That match was not a coincidence. It served as a genuine confirmation that the correspondence was capturing real, correct physics, rather than simply being an elegant but empty mathematical curiosity. Hawking radiation, the faint thermal radiation that quantum mechanics predicts, should gradually be emitted by black holes over extremely long timescales. carries this entropy puzzle to its sharpest and most uncomfortable point. A black hole that slowly evaporates through Hawking radiation begins its life carrying a large amount of entropy. Entropy that should, in principle, be carried by the information content of whatever matter originally fell into it. As the black hole evaporates, that information should, in principle, eventually find its way back out, encoded somehow in the Hawking radiation itself. But Hawking's original calculation, carried out in the 1970s, suggested that the emitted radiation was exactly thermal, carrying essentially no information at all about whatever had originally fallen in. That result, taken at face value, would mean the original information had simply been destroyed. Destroying information outright, however, is forbidden by the basic rules of quantum mechanics. This tension is known as the black hole information paradox, and it has occupied theoretical physicists for decades. The holographic correspondence offers a possible resolution to this paradox, because a black hole is dual through the holographic dictionary to an ordinary quantum system living in flat space. And because quantum mechanics fundamentally preserves information, the original information must, in principle, come back out somewhere in the Hawking radiation, even if tracking exactly how and where it does so remains extremely difficult in practice. The anti-de Sitter conformal field theory correspondence essentially guarantees that black hole evaporation must be unitary, meaning information preserving, because the whole process maps directly onto a perfectly ordinary, unitary quantum mechanical process taking place on the other side of the holographic dictionary, working out the precise details of exactly how that information makes its way back out, and what that process implies about the detailed semi-classical geometry of an evaporating black hole, remains a genuinely active area of ongoing research. In recent years, this particular research program has produced some genuinely surprising results, including the discovery that a certain kind of geometric calculation involving objects called replica appears to correctly reproduce the expected behavior of the information content carried by Hawking radiation, tracked carefully as a function of time. This result, worked out by Ahmed Almi, Netta Engelhardt, David Marolf, Henry Maxfield, and several collaborators, has been widely described as a significant step forward in understanding the black hole information paradox. Quantum simulation could eventually play a meaningful role in testing these ideas as well. If researchers could build a quantum system genuinely holographically dual to an evaporating black hole, and could run that system long enough to actually observe information making its way back out in the analog of Hawking radiation, they could, in principle, test the replica wormhole calculation directly against real experimental data rather than purely theoretical argument. That remains a considerably more demanding experiment than anything currently possible with existing hardware, but it sits squarely on the same conceptual roadmap as the original wormhole experiment. The common thread running through all of these separate research programs is the use of quantum information theory to understand gravity, not simply as a convenient calculational tool for working out things that were previously intractable, but increasingly as a kind of language for expressing what gravity fundamentally is. At the deepest level anyone currently understands, the holographic principle suggests that gravity may not be a fundamental force in quite the same sense that electromagnetism and the nuclear forces are fundamental forces. It might instead be an emergent phenomenon arising out of the entanglement structure present in a quantum system living on the boundary of space-time. If that turns out to be correct, then understanding quantum information is not merely useful for studying gravity as a separate subject. It would be, in some genuine sense, the same thing as studying gravity directly. That is a genuinely radical idea, and it has not been proven. The holographic correspondence as currently understood, is a precise mathematical duality that applies to specific, well-defined kinds of spacetime, not a fully general derivation showing that gravity emerges from quantum information in every possible setting. Extending the idea cleanly to our actual universe, with its de Sitter geometry and its measured cosmological constant, remains a major unsolved problem. The detailed connection between the geometry of spacetime in the interior, sometimes called the bulk, and the entanglement structure on the boundary is still being worked out in considerable mathematical detail. Tensor networks, mathematical structures designed to encode patterns of entanglement in an explicitly spatial arrangement, have been proposed as useful toy models for how spacetime geometry itself might emerge from underlying entanglement. But making those particular models fully precise and genuinely testable remains an active area of ongoing theoretical work. What can be said with real confidence is that the connection between quantum information and gravity is deep, and it is real. It shows up directly in the black hole entropy formula. It shows up in the holographic entropy bound. It shows up throughout the black hole information paradox and the various proposed resolutions to it. It shows up throughout the anti-de Sitter conformal field theory correspondence in all its many applications. It even shows up in the so-called area law governing entanglement entropy in ordinary quantum field theories, a mathematical pattern that closely mirrors the area law governing black hole entropy itself. These are not a collection of isolated coincidences. They read, taken together, as converging signs pointing toward a genuine relationship, running through the deeper mathematical structure of both theories. The experiments currently being carried out using quantum computers represent attempts to make that abstract relationship tangible, to build something inside an actual laboratory that manifests the holographic dictionary as a real physical phenomenon, rather than leaving it as a purely mathematical correspondence sitting on paper. To watch information behave the way it would behave if space-time geometry were, in some genuine physical sense, real and constructible, whether any specific experiment carried out so far has actually achieved that goal remains a question the field is still actively arguing about. Whether the 9-qubit wormhole signal was genuinely gravitational, or merely an artifact of a commuting system dressed up to look gravitational. Whether the sparsified SYK model preserved enough of the genuine holographic structure to count as a meaningful test in the first place. Whether the 5000 qubit vacuum simulation tells researchers something real about the ground state of our actual universe, or only about the behavior of one-dimensional Ising models held at low temperature inside a laboratory. These are not weaknesses of the field, even though they might sound that way. Describe this plainly. They represent the field genuinely working in real time. The same careful process that produced the Berkeley critique will, in time, produce the next generation of better, more carefully designed experiments. The same uncertainty currently surrounding the wormhole interpretation is itself motivating the development of validation, tools that will make the next generation of quantum gravity experiments considerably more reliable than the current one. There is one more dimension to this story worth sitting with, one that lives at the boundary between physics and philosophy. It concerns what it actually means for a quantum computer to simulate a physical system in the first place. When physicists say that a quantum processor simulated a wormhole or simulated false vacuum decay, they are using the word simulate in a very specific technical sense, one that differs in an important way from its everyday meaning in ordinary usage. A simulation is understood as a model, an approximation, a kind of stand-in for something real. A flight simulator does not actually fly. A climate model does not actually contain an atmosphere. The simulation represents something real without literally being that thing. In quantum simulation, the situation turns out to be considerably more subtle than that everyday picture suggests. The quantum system actually running on the processor is, in every meaningful sense, real. The qubits are genuine physical objects. The quantum states they occupy are genuine quantum states. The entanglement between them is genuine entanglement, not a representation of entanglement. The measurements taken on them are real measurements, producing real experimental data. Whatever is happening inside the quantum computer is not, strictly speaking, a representation of physics standing in for the real thing. It is physics, happening directly. The deeper question, then, is whether the physics happening inside the quantum computer is the same. Physics as whatever physical system is actually being targeted by the experiment. And that turns out to be a question entirely about mathematical correspondence, about whether the relevant Hamiltonians genuinely match, about whether the degrees of freedom map onto one another correctly, about whether the observable quantities on each side of the correspondence truly correspond to one another in the way the theory claims they should. This distinction matters quite a lot, because it changes what kind of knowledge a quantum simulation can actually provide. A classical simulation of a physical system can tell researchers what a particular set of mathematical equations predicts, but researchers still have to separately trust that those equations are themselves correct. A quantum simulation of a genuinely equivalent physical system, by contrast, can tell researchers what the underlying physics actually does, because in that case, researchers are not merely running the mathematics that describes the physics. They are, in a real sense, running the physics itself. If the quantum system really is equivalent to the system under study, then the resulting simulation is not an approximation at all. It is the real thing, simply made accessible in a more convenient and controllable form. This basic idea traces back to Richard Feynman's original proposal for quantum computing. In a well-known 1982 talk, Feynman pointed out that simulating quantum mechanics on an ordinary classical computer is exponentially hard, because the size of the state space describing a quantum system grows exponentially with the number of particles involved. A classical computer attempting to simulate a system of 100 quantum particles would need to track to raise to the power of 100 separate numerical values, a quantity far beyond what any classical computer that exists, or could ever plausibly be built, could realistically handle. But a real quantum system made up of 100 quantum particles simulates itself perfectly and efficiently, simply by existing and evolving according to its own natural dynamics. The basic idea behind quantum simulation is to harness a controllable quantum system to carry out exactly the kind of simulation a classical computer fundamentally cannot if that underlying program works exactly as intended. Then a quantum simulation of a traversable wormhole is not merely a model of a wormhole sitting somewhere off to the side. It is, in the relevant technical sense, a wormhole, not located in our own space-time, and not anywhere a person could ever physically visit or directly observe, but located in the holographic dual space described by the correspondence, a space that is, according to the mathematics, just as physically real and mathematically identical to the space-time described by the corresponding gravitational theory. The qubit that appeared to teleport through that 9-qubit processor in Santa Barbara did not merely model the act of traversing a wormhole. If the holographic correspondence genuinely holds for that particular system, it traversed a wormhole. In the only sense that ultimately matters physically, that is a remarkable claim. And it is precisely the claim the Berkeley critique placed under serious pressure. If the Hamiltonian actually used in the experiment was not, in fact, genuinely holographically dual to a gravitational system containing a traversable wormhole, then the qubit involved did not traverse a wormhole at all. It traversed an ordinary quantum circuit. Those two outcomes are not the same thing, even though, from the outside, the raw experimental data looks identical either way. The word simulate, used in this quantum context, is only ever as meaningful as the underlying correspondence connecting the simulator to its intended target. When that correspondence is exact, simulation effectively becomes realization. When the correspondence is only approximate, or when it holds only within certain narrow limits, the resulting simulation remains, in the end, just a model. Much like any other model used anywhere else in physics, this is a genuinely difficult conceptual issue, and it is not the kind of thing any single experiment is going to resolve on its own. Resolving it properly requires a careful, theoretical characterization of exactly which physical quantities are preserved under the holographic dictionary, and which are not. It requires a clear understanding of the precise limits of validity for the correspondence itself, the specific places where the quantum system and its gravitational dual quietly begin to behave differently from one another, and it requires experiments specifically designed to probe those limits directly, rather than experiments designed only to confirm, once again, that the correspondence holds in the comfortable regime everyone already knows it works in. The wormhole experiment was, in its original conception, an attempt to do exactly that, to probe the holographic correspondence in an entirely new regime, the regime of traversable wormholes and genuine quantum teleportation, a regime nobody had ever previously been able to reach inside a controlled laboratory setting. The fact that the attempt ran into serious problems connected to its sparsification step does not mean the underlying ambition behind it was wrong. It means the available tools were not yet fully adequate to that ambition. Those tools are steadily improving. The theoretical understanding of what actually makes a quantum system genuinely holographic, as opposed to merely resembling one in certain superficial respects, continues to sharpen with each passing year. Experimental capabilities continue to advance. Validation methods continue to be developed, slowly but steadily, by researchers across the field. The deep questions sitting at the heart of this entire program, questions about the relationship between quantum information and space-time, about whether the universe people actually inhabit is fundamentally holographic in nature, about whether our own vacuum is genuinely stable, and about what ultimately happens to information when it falls into a black hole, are not the kind of questions that get settled inside a single paper, or by a single experiment, however dramatic that experiment might appear at first glance. They are questions that will be answered, if they are ever answered at all, through a long, gradual accumulation of experimental results and theoretical advances, each one moving the boundary of what is currently known forward by some small additional step. That process is already underway. It produces controversy along the way, because genuine progress at any real scientific frontier tends to produce controversy as a natural part of the process. It produces corrections to earlier claims, because that is simply what careful science looks like whenever it is genuinely functioning as intended. And gradually, it produces better experiments, better underlying theories, and better tools for connecting the two together more reliably. The 9 qubits humming quietly inside that small refrigerator in Santa Barbara were a beginning, not an ending. Consider, for a moment, how unusual this entire situation actually is, set against the broader history of quantum gravity as a field of study. For most of that long history, quantum gravity research was purely theoretical. There was no experimental input available at all, and in a very real sense, there could not be. The energy scales at which quantum gravitational effects become significant sit far beyond anything any particle accelerator currently in existence, or any particle accelerator that could plausibly ever be built could hope to reach. The only available evidence came from careful thought experiments and from arguments about mathematical consistency, worked out entirely on paper. The arrival of quantum simulation has begun, gradually, to change that long-standing situation, not by granting direct access to genuine quantum gravitational energy scales, since that particular gap remains as vast as it ever was, but by granting access, for the first time, to systems that are holographically dual to gravity, systems capable of exhibiting the recognizable signatures of gravitational behavior through the correspondence, systems that can actually be controlled and measured inside a real laboratory. This is not quite the same thing as directly observing quantum gravity in action. It is, perhaps, the next best available alternative, a window into gravitational physics, opened through an unexpected side door that nobody had even realized existed until Maldacena pointed toward it. A door that nobody could actually walk through until quantum computers finally became sophisticated enough to run the right kinds of models. That window is open now. The view through it remains genuinely blurry in places. Some of what researchers currently believe they are seeing through it may, on closer inspection, turn out not to be there at all. But the window itself is real. The view through it continues gradually to improve, and the physics sitting on the other side of it remains among the deepest and most fundamental physics there is to study. It is worth taking a moment to think about the broader implications of everything described here, because this quiet, ongoing program is not only changing physics in a narrow, technical sense, it is gradually changing what kind of evidence researchers can even have about fundamental reality itself. And that shift is genuinely worth examining carefully and patiently. For most of the history of science, experimental evidence has come in essentially to recognizable forms. Direct measurement, where researchers build an apparatus that interacts with the phenomenon under study and read off a result. An indirect measurement, where researchers instead observe the effects of something they cannot access directly and infer its underlying properties from those observed effects. Nobody can directly observe an electron's wave function, but researchers can build a double-slit apparatus and observe the resulting interference pattern. Nobody can directly observe a quark sitting inside a proton, but researchers can fire electrons at protons at high energy and observe how those electrons scatter. The inference connecting an observation to the underlying reality it points toward is always mediated by theory. But across most of the history of physics, that mediation has been well enough understood that the resulting inference could be trusted as essentially solid. Quantum simulation introduces a genuinely new mode of evidence into this picture. Researchers are not directly measuring the system they are actually interested in studying. Instead, they are building an entirely different system, one that is theoretically equivalent to the system they care about, and they are measuring that proxy system instead. The resulting evidence about the original target system is mediated not only by an ordinary theory about how to properly interpret measurements, but also by a separate theory establishing the equivalence between the proxy system actually being measured and the target system researchers ultimately care about. This is not, in every respect, entirely new. Computer simulation has already served as a form of proxy evidence for decades across other fields. Climate models, molecular dynamics simulations, and lattice quantum chromodynamics calculations all rely on classical computers to simulate systems, too complex to solve through analytical methods alone. The outputs of those simulations are routinely used to make predictions about real physical systems. Predictions that are then compared directly against observations. Those simulations are taken seriously as a genuine form of evidence. But quantum simulation differs from all of this in one crucial way. Classical simulations can, in principle, always be independently verified. Researchers can check the underlying code line by line. They can run test cases where the correct answer is already known in advance. They can compare results against entirely independent calculations carried out by other means. The simulation, at bottom, is simply mathematics. And mathematics is, in this sense, fully transparent and open to inspection. Quantum simulation is not transparent in quite that same way. The calculation itself happens inside the quantum state of the physical hardware, distributed across the correlations, linking together thousands of entangled qubits. And there is no efficient way to extract and fully examine that complete state without destroying it in the process of measurement. This opacity is a fundamental, built-in feature of the technology, not an incidental flaw that better engineering could simply eliminate. It is the very same feature that makes quantum computers powerful in the first place. The quantum state encodes exponentially more information than any classical description of the same system could capture. Researchers cannot extract all of that information efficiently, and that same fundamental limitation means they also cannot fully and independently verify whether the calculation taking place is actually doing what they believe it is doing. The theoretical physicist John Bell, well known for Bell's theorem and the associated Bell inequalities, once observed that the most important word in science is not truth, and not proof, but rather the word correlate. What is it that researchers actually know? What is it that has actually been measured? And how, precisely, do researchers know that those two things are genuinely correlated with one another? The verification problem running through quantum simulation is, at bottom, really just a sharpened and more urgent version of that same basic question. There is a signal. There is a theory describing what that signal should mean. What exactly correlates the observed signal to the underlying physical reality the theory claims to describe? And how confident can anyone reasonably be that the correlation genuinely holds? For the wormhole experiment, that correlation was mediated by the holographic dictionary itself, a precise mathematical correspondence, and by the sparsification process layered on top of it, a process that introduced its own additional uncertainty into the chain. The Berkeley group found that the sparsification step had, without anyone fully realizing it at the time, broken that correlation in an important way. The underlying dictionary itself was correct, but the particular system being translated through that dictionary was not. In the end, the system the original team believed it was. For the false vacuum simulation, the correlation involved is considerably more direct. The underlying physics of the Ising model is well understood, and the mapping from the Ising model's dynamics to the physics of false vacuum bubble nucleation is theoretically clean and well established. The correlation genuinely holds within the specific regime the experiment was actually conducted in, but it holds reliably only for one-dimensional dynamics. The further correlation between that one-dimensional simulation and the full three-dimensional false vacuum dynamics that would govern our actual universe remains a theoretical extrapolation, not yet a direct, verified correspondence in its own right. In both cases, the experiment ultimately gives researchers something genuinely real data gathered from a real quantum system. What anyone can responsibly do with that data depends entirely on the quality of the theoretical bridge connecting the quantum system actually measured to the physical phenomenon researchers genuinely care about. Building better theoretical bridges of this kind is, in the end, just as important to the field's future as building better quantum hardware itself. The history of quantum mechanics offers its own kind of caution here. A reminder of how genuinely difficult it has always been to predict in advance. what a new, experimental technology will eventually reveal. When Paul Dirac worked out the relativistic quantum mechanics governing the electron back in 19, his mathematics required the existence of a particle sharing the electron's mass, but carrying the opposite electric charge. He initially doubted whether such a particle could possibly be physically real. 2 years later, Carl Anderson found exactly that particle, the positron, captured in cosmic ray tracks. The mathematics, in that case, had told the truth all along. Quantum simulation of holographic gravity might, in time, follow a broadly similar path. The underlying mathematics of the holographic correspondence might be telling researchers something genuinely real about the deep structure of space-time, something that future quantum simulation experiments will eventually confirm in a way that becomes essentially impossible to reasonably dismiss. Or the mathematics might instead turn out to describe a precise correspondence that holds reliably in certain specific, carefully chosen settings, without ever fully generalizing to the actual universe people happen to live in quite the way many researchers currently hope it will. The coming experiments will probably not answer that particular question definitively, at least not for a long while yet, but they will steadily narrow the range of possible answers. They will help clarify which specific predictions of the holographic framework turn out to be true, and which do not, at least within whatever regimes remain experimentally accessible. That, in the end, is simply how this kind of science tends to work. Not through any single, decisive experiment that settles everything at once, but through a slow, progressive narrowing of the space of what remains genuinely possible. The physicists actually carrying out these experiments understand this well. The goal was never to prove, in any single paper, that space-time is conclusively holographic. The goal has always been to probe the holographic dictionary inside a regime that had never before been probed, to find out what it genuinely predicts, and to compare those predictions carefully against whatever reality turns out to show. That is a research program that will likely take years, quite possibly decades, and will involve hundreds of individual experiments and thousands of theoretical papers along the way. It is already happening now, imperfectly, with all of its accompanying controversy, its validation problems, and the persistent gap between dramatic, experimental claims and what the underlying data can genuinely support. But it is happening. The 9 qubits inside that small refrigerator in Santa Barbara, the 5,564 qubits running inside the very different machine in and whatever comes after them, with more qubits, better error correction, and steadily sharper theoretical frameworks. Each one is, in its own quiet way, asking the universe a question it has never quite been asked before from inside an actual laboratory. Some of what comes back in response will turn out to be real. Some of it will turn out to be artifact, a shadow cast by simplification rather than a genuine signal from the underlying physics. Learning to tell the difference, with all the rigor that distinction genuinely deserves, is the patient work of the next era of experimental physics. It is slow work and careful work, and the headlines occasionally get ahead of the underlying facts before the field has a chance to catch up. But the questions themselves remain genuine. The tools available for answering them continue, gradually, to improve. And so far, at least, the universe does not appear to be refusing to answer.